Okay, number 10 on page 460, the directions are tell whether or not this is an identity. Now they're trying to trick you because they're hoping you're going to go, I'm going to divide out the 2, but that is not possible when the 2 is in the signed function. Now we haven't done this identity yet, but if you look on your pink sheet, you would see there's an identity for sine 2x, and it's 2 sine x cosine x. Now you weren't expected to use this. They just wanted you to realize you can't divide out that 2. But let's just say you did do this. You're trying to check if this equals sine x according to the directions. And as you could see, it would come out to sine x cosine x. So that is not an identity. Okay, number 51, the directions are prove the identity, which means you can only work on one side, and you're trying to get it to equal the other side. And I looked at this at first, I could picture something to do on each side, but I decided to go with the more complicated looking side and try to get it to look like the simpler side. So to do that, first I thought I'll factor this to 1 minus cosine squared x times 1 minus cosine squared x, and then the sine x is still there. Now you can see how working vertically you can see what follows from what. That's why I recommend working vertically. Now off to the side I want you to recall sine squared x plus cosine squared x equals 1. And in this problem I have a couple of 1 minus cosine squareds, so I'm going to subtract this to the other side. Sine squared x equals 1 minus cosine squared. So here's 1 minus cosine squared and here's 1 minus cosine squared. So in place of those, I'm going to put a sine squared for each one. So I have sine x, I have 2, 4, 5 of them. And now it equals the other side. I'm going to rewrite that. If you'd like to do these properly, like if you're going on to college, notice how I kept my equal sign all the way through, showing that that side stayed equal all the time. That's why I did that pink work off to the side, because that doesn't flow from the rest of the work. Once they're equal, if you want, you can say QED. Quod erat demonstrandum, which is Latin for thus it has been shown, or thus it has been demonstrated. So mathematicians sometimes put that to show they finished proving something. In number 54, it gives you a list of different choices and you're trying to prove that this equals one of them. I'm not really sure which one it is at first, so I'm just going to start by rewriting secant as 1 over cosine. So I'd have 1 over cosine squared, because the secant is squared. And then for cosecant, 1 over sine squared, for cosecant squared. I think I'll try to get a common denominator. So that means I'll multiply this one by sine squared over sine squared. And I'll multiply this one by cosine squared over cosine squared. So what I'd end up with is this times 1 would be sine squared x. Both of them are going to have the same denominator now, which will be sine squared x cosine squared x. And then I have the plus from right here. Plus, and then cosine squared. I don't think I like having that circle around my plus anymore. Alright, at least you can see that the top here equals 1. That's like kind of the mother of all trig identities right there. So 1 over sine squared x cosine squared x. At this point, I'm just going to stop and look at those choices. Oh, this does look like one of them. It looks like answer A, because I can break this down to 1 over sine squared times 1 over cosine squared, which would be cosecant squared times secant squared. And that is answer A if I just use the commutative property of multiplication to rewrite this as secant squared cosecant squared. Okay, number 57, same thing as the last problem I did. You've got a bunch of choices and you're trying to figure out which one this is equal to. So I think that I will change it to cosines and sines. Oh, the bottom ones have a common denominator. I think I'll add them together. This does not look like it's going to equal any of those choices, though. Okay, so I can invert this because it's 1 over a fraction. Now, how can I get this to equal one of these things? Maybe I'll try multiplying by 1 plus sine x. I'm just guessing. Like I've told you guys before, you can try a lot of different things. Okay, let's see. If this puts me back to the original problem, I'm going to be mad at myself. Okay.
Can we try cosine minus, or plus 1? Cancel out the top.
Okay, that's answer B. Let me go through some of these steps and explain what I did. Okay. First I multiplied the cosine times 1 and the cosine times sine to get the numerator over there. And then I multiplied these denominators and to come up with this difference of squares. Then I factored out a cosine. This cosine and this cosine I took out front. So that means I need a 1 right there, so if I'd multiply it back in, I'd still get the first cosine. Then I divided one cosine out. I have this cosine divided out with one of those, and that's how I got 1 plus sine x over cosine x. Then I could break this down into 1 over cosine plus sine over cosine, which is secant x plus tangent x. Okay, now that I did 57 one way, it occurred to me that I could have done it an easier way. So let me show you that way. A lot of times if you have a minus or plus, you can multiply by the conjugate. And it will take you to one of the Pythagorean identities. So now on the numerator, I'll have secant x plus tangent x. And in the denominator, if I multiply that out, I'd get secant squared x minus tangent squared x. Okay, thinking about my Pythagorean identities. Oops, I'm going to write over here to the side. I have 1 plus tangent squared x equals secant squared x. So 1 equals secant squared x minus tangent squared x. So if I come back over here, my denominator is 1. So I have secant x plus tangent x over 1, and that's a much faster way to do that problem.